This is Lesson 1 in Chapter 5. We're looking at polynomial functions today. We call a polynomial a monomial or a sum of monomials. A monomial is one term. And the greatest degree among the monomial terms is known as the degree of the polynomial. The degree of the polynomial. We don't add the powers. We look for the highest or the greatest degree among all the terms. We say we have a polynomial function when a polynomial is in one variable x, a polynomial function. And we have standard form whenever we write and arrange the terms by the degree in descending numerical order. That's going to be standard form of a polynomial. So here you see x to the nth power and then one power less than the greatest power all the way down to x to the first, and then our final term would simply be a constant or a number. When we have a point where the graph of the function changes direction from up to down or from down to up, we call that a turning point. So we have a turning point whenever we go from up to down or down to up. And then our last vocabulary word is going to be the end behavior of the polynomial. The end behavior is the direction of the graph of the function as you move toward the infinities, either to negative infinity toward the left or positive infinity toward the right. We're moving away from the origin. That's called our end behavior of the function. Let's classify polynomials. We can classify a polynomial by the degree. If the degree is 0, we call that a constant term. Say -7, because if you think about having a polynomial whose variable is x, a polynomial function, when the degree is 0, 7x to the 0 is the same thing as saying -7, since we define x to the 0 is just a 1. So a constant term is a polynomial function whose degree is 0. When the degree is 1, that would be a linear polynomial. An example, 2x plus 5, because our polynomial function is a variable of x and the power on x is 1. We have a quadratic function when the highest power is degree 2. So we can name a polynomial as quadratic when the degree of the polynomial is 2. We say we have a cubic polynomial when the degree is 3. And I'm thinking of an example, 5x cubed minus 2x. When the degree is 4, we'll call that a quartic, Q-U-A-R-T, quartic for quadrant, 4, quarter, x to the 4th plus 3x squared minus x plus 5 is my example. And then finally, a 5th degree polynomial is called a quintic. When I'm naming it by degree, quintic, x to the 5th minus x squared plus 3x is my example here. Not only can we name polynomials by the degree, but we can also name them by terms. Let's say, for example, we had a polynomial function 8x cubed. That's a single term. Single meaning mono is my prefix, so a monomial is one term. Notice that the term is 8x cubed. So multiplication is holding my monomial together. When I have a term like x squared and then I subtract 8x, that has two terms. The subtraction is separating my first term, x squared, from my second term, 8x. So x squared and 8x are my two terms. The operation is subtraction. When there's two terms, that's known as a binomial. A binomial. When we have three terms, that would be a trinomial. And you can write an example for yourself. And then we have four terms or more. We're just going to name that as polynomial. Poly means many, so polynomial. And we want a three-termed polynomial and four or more terms to get a polynomial. So let's give this a try. We want to write each polynomial in standard form and then name the polynomial by the degree and by the number of terms. So here I want to put the highest term, highest degree first. That's 5x to the fourth. And then we have a positive 4x squared. And then we're subtracting 3x. So the highest degree is 4. And we said on the first slide that quartic is a fourth degree. And there are three terms. So this would be a quartic trinomial. In part B, x cubed is our highest degree, so that's the first term, minus 3x squared, and then plus the linear term, and then plus the constant. So the highest degree has a name cubic, since 3 is cubic, and there's four terms, so we're going to call that a cubic polynomial. In part C, that's relatively simple. They're just out of order. 3x plus 8. X to the first power is a linear term, and there are two terms, so we have a linear binomial. And then part D, there's only one term, so we know that's a monomial, but the degree is 7th, so we're just going to, the degree is 7, so we're just going to name that by the degree and say it is a 7th degree monomial. So the degree of a polynomial will affect the shape of its graph, and it'll also determine the maximum number of turning points. It also affects the end behavior of a function. When we have an even function like power 4 or power 2, the graph starts and stops in the same location. This one is up, and this one is down and down. Notice that x to the fourth is a positive leading coefficient, and negative x squared is a negative leading coefficient. That's why when the coefficient is positive, the end behavior is up, and when the leading coefficient is negative, the end behavior is down and down. But this happens on an even function. So on this even function, we have 1, 2, 3 turning points, and our behavior is up and up, so it's positive infinity. Here we're down and down, or negative infinity, with only one turning point. So 3 turns, because the power was 4, we have one less turn than the highest power, and the end behavior is up and up since we had a positive 1x to the fourth. And on the second one, we had one turn, and we had one turn because the power was 2, so 2 minus 1 is one turn. The end behavior was down on the left and down on the right because we had a negative 1x squared. Let's look at the odd functions. When the power is odd, the behavior is the opposite. If it starts low, it'll end high. If it starts high, it will end low on an odd-powered function. When the leading coefficient is 1, you start low, end high. When the leading coefficient is negative, in this case it's negative a half, we do the opposite. Start high, end low. So our end behavior is down and up, or up and then down. And the turns, since the power is 3, 3 minus 1 would give us 2 turns, and we can see those 2 turns, 1 turn here and 1 turn here. And the behavior started down and ended up. And then on the last one, we had 3 for the power. So again, 2 turns, but this time we had a negative 1/2 for our leading coefficient. So that graph started high and ended low. Let's analyze this next example, in example 2. We want to look at the leading term of this polynomial. It's negative 4x cubed. So that's our leading term. We want to know what the end behavior is and then kind of explain it. So we know if the leading term is negative 4x cubed, then our a value is negative. And the power is 3. So the a is negative and the degree is 3. It's an odd function. So normally an odd function begins low and ends high. But this one is negative, so it's going to do the opposite. This one is going to begin high and end low. So our graph is going to go up on the left, and then it's going to end down on the right. You can think of that as x goes to the extreme left. As x goes left, y is getting very large. And as x goes to the right, y is going to go down to negative infinity. Another thing I like to do is make a table real quick just to get a few extra points. If we substitute negative 1 into our original function up here, the y value will be 13. Substituting 0, we end up with 7. And substituting positive 1 will arrive at 5. So we know 3 extra points, 3 points on our graph. By plotting them, negative 1, 13, 0, 7, and 1, 5, and keeping that serpentine shape, that's up to down, we'll sketch the smooth, continuous curve looking like that. So we got a cubic polynomial that started on the high side and ended up on the low side. Let's try a few more graphing with x cubed minus 1. So if we know that x cubed minus 1 is just the parent graph shifted down 1 unit, we know the a value is 1, and the cubic graph is going to start low and it's going to end high. And by making a table to get a few extra points, I'm going to use negative 1, 0, 1, and 2. And my y values are going to be negative 2, negative 1, 0, and 7. So we're going to graph those, negative 1, negative 2, 0, negative 1, 1, 0, and 2, 7. So we have the cubic polynomial that resembles that. On the next one, our a value is -1, so it's going to do just the opposite of example 3. And we would expect it to start high or start on the up and end low or end on the down. And again, just making a table and choosing just a few x values to substitute into the function. We'll find a few y values. And we know the behavior of the graph. So at -1, we have 2. At 0, -2. At 1, -2. And then 2, -4. So we've got a little issue here in between 0 and 1. So how do they behave? If it's got to be cubic, we need a little hump right there to get over the point. It's not going to be a straight line straight across. It's going to have that shape of a serpentine type graph. If you need, you can grab your calculator and verify that it has that funny little hump right there. And then our last example, we can actually use differences between the y values to determine the degree of the polynomial. So what I want to do here is I want to look at when x is -3, I'll get a green here. So when x is -3, y is 23. When x is -2, y is -16. And at -1, so I'm just creating the table so you can follow my thinking in this process. So these are my x and y values here. And then I want to take the difference between the two y values. So -16 minus 23, that difference is -39. And -15 minus -16, the difference is +1. And -10 minus -15, I have a difference of 5. In the next two, my difference is -3. And then this difference is +1. And this difference is 41. So we're going to say this is the first differences. Now notice they're not the same. So let's try that again. The difference between -39 and +1 is 40. The difference between 1 and 5 is 4. Between 5 and -3 is -8. Between -3 and 1 is 4. And between 1 and 41 is 40. So again, you see in our second differences, those numbers are not the same. So one more time, let's find the third differences. So 40 and 4, the difference is -36. Between 4 and -8, the difference is -12. The difference between -8 and 4 is +12. And between 4 and 40 is 36. So this is our third difference. The third differences. They're not the same. So let's try one more time. The difference between -36 and -12 is 24. This difference is also 24, and the last one is 24. So we found out that the fourth differences all resulted in 24. They're the same. So the fourth differences tell me that since they're the same number, the values in the table represent a fourth degree quartic polynomial function. We could write that in a sentence. The values represent a fourth degree. We could also call that quartic, Q-U-A-R-T-I-C, quartic polynomial. because the fourth differences were the same. And that, my friends, is the end of the first lesson in Chapter 5.